This is a nice review example on angular kinematics. And real quick, I want to post a link back to where the angular kinematic formulas came from. And I want to post a link back to where the relationship between speed and angular velocity, tangential acceleration, and angular acceleration came from. Okay, let's get started. So I have a grinding wheel with a radius of 15 centimeters. It has an initial velocity given in radians per second. That's nice. And it slows down with a constant angular acceleration of 250 radians per second squared and comes to rest. So one important point about this problem is if I'm going to consider the rotational velocity to be positive, to be slowing down, the angular acceleration must be negative. So that's going to count as a negative 250 radians per second squared. I want to find out how long it takes for this wheel to come to rest. And so I pick a kinematics formula that's going to get it done for me. My final angular speed is equal to the initial plus angular acceleration times how much time has gone by. And my final here is 0 because I'm talking about it coming to rest. So I have 0 equals 1,000 radians per second minus 250 radians per second squared times how much time has gone by. And I can see that I'm going to get exactly 4 seconds for this disk to come to rest. Part B, how many turns does it complete during this process? So I would go to my first kinematics formula for this. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And theta is really what I'm after. If I define my initial angle to be 0, which is perfectly fine. So this is just like painting a spot on the disk at theta equals 0 when t equals 0. And I just want to know how many turns does it do after that. If you prefer, you could subtract theta naught from both sides and say you're solving for delta theta. I just find it simpler to plug the 0 in there. And so I get omega naught t, so that's 1,000 radians per second times how much time went by. That's 4 seconds. And then my second term is negative because alpha is carrying that minus sign. 250 radians per second squared times t squared. And when I crunch the numbers here, I get 2,000 radians. But I still have to do a unit conversion. So I'm going to go from radians to rotations. I have one rotation for every 2 pi radians. And when I complete that conversion, I get 318 turns. Part C, calculate the initial speed at the edge of the wheel. For this, we're going to use V equals R omega. And my wheel has a radius of 15 centimeters or 0.15 meters. And my initial angular speed is 1,000 radians per second. So I get 150 meters per second at the edge of the disk. Part D, calculate the tangential acceleration at the edge. Okay, A tangential is equal to R alpha. All right, and this is just telling me how fast the speed is changing at the edge of the disk. And I should probably keep the direction on this thing. So I'm going to have a minus sign, 0.15 meters, 250 radians per second squared. And when I do that, I get negative 37.5. And at this point, I need to remember that radians are unitless, and I can disappear them whenever I like. And I get meters per second squared. So I've got this speed of 150 meters per second. And then A tangential tells me how fast that's slowing down. Part E, calculate the initial radial acceleration at the edge. The radial acceleration is the centripetal acceleration. It points to the center to keep this thing moving on a circular path. So I'm going to pick the formula R omega squared. You could use V squared over R if you like. And I get 0.15 meters for the radius. And then omega in the initial state was 1,000 radians per second. And that all has to be squared. Remember, radians are unitless, so I get the correct units of meters per second squared out of this. And when I crunch the numbers, I get this enormous value of 150,000 meters per second squared at the edge of the grinding wheel.